We will be continuing our lecture into 6.10, which is the Carnot heat engine. Yeah, so I've explained to you the Carnot cycle earlier. So now let's look at the Carnot heat engine itself. So textbook, we are looking at page Carnot heat engine at page 301. Yeah, okay. So the Carnot heat engine is the most efficient of all heat engines operating between the same high and low temperature reservoir. I've just explained to you like earlier. So this Carnot heat engine does not have any irreversibilities. So it is a perfect. Okay. From the previous lesson, we know that efficiency is actually 1 minus QL over QH. But then for a Carnot heat engine, we don't use Q, we don't use the heat, but we use the temperature instead. So what is this REV? REV is reversible. So 1 minus TL over TH. Yeah. Okay. So let's look at this example. No heat engine can be a higher efficiency than a reversible heat engine operating between the same high and low temperature reservoir. So we have three heat engines here. Okay, let's analyze them. This is a reversible heat engine. It will be 70%. Irreversible will always be lesser than the reversible. So in this case, it is 45%. And then the impossible heat engine will be anything that is higher than the 70%. Yeah. Okay. This is a summary. Okay. Let's look at it. Yeah. Whatever that you've calculated here. Yeah. Whatever that you've calculated here, the efficiency of any heat engine, yeah, if it's equal to the reversible, equal to this value, yeah, equal to this value, then it is a reversible heat engine. Anything that is lesser, then it is irreversible heat engine. Means there are irreversibilities. And anything greater, it is impossible. So this is another way also to see on papers, yeah, on calculation, whether it's an impossible heat engine or whatever the scenario is, even before signing it. Yeah. Now let me go into quality of energy. According to Carnot, the quality of energy is determined by the temperature difference itself. If the temperature difference is greater, okay, let's look. Like in this case, this is 303, the baseline is 30 TL. If you put here 925, yeah, your efficiency is 67. The same thing if you repeat to 700, your efficiency is only 56.7. So in another word, the quality actually increases with the thermal energy itself. So that is what that this statement explains this question here. Yeah. Okay. So how do you increase the thermal efficiency of Carnot heat engine? Is by increasing the temperature difference. What about the heat engine? Heat engine, the formula does not look at temperature, but it looks at the heat, the Q. Yeah. So that's the difference. Okay. Now last part of the chapter would be the Carnot refrigerator heat pump. Okay, now before even me going into this, let me just solve one question for the heat engine. Okay, let's look at this question. We'll just make the screen a bit smaller. Okay, the Carnot heat engine shown in figure 6.48 receives 500 kilojoule. This is from the textbook, yeah? Receives 500 kilojoule heat per cycle. Okay, the Q, from a high temperature source of 652. Rejects heat to the low temperature 30 degrees. Yeah. So determine A, the thermal efficiency of Carnot. So Carnot, remember, it uses temperature. Yeah, uses temperature. So look at the formula. It uses 1 minus TL over TH. So you get 0.672. Okay. Question B, the amount of heat rejected to the sink. So what is the amount of heat rejected to the sink? So this Carnot heat engine actually converts 67.2% of the heat that's received to work. So using the previous formula, you can actually find what is the QL, isn't it? Because you are given QH. QH is 500 kilojoule. Yeah. So remember, all this one is given in Celsius. It's all in Celsius. You need to change them into Kelvin. Yeah, you cannot just use Celsius. So that's how this is working here. TL over TH multiply with the QH reversible. So you get 164. So we have answered this question. Now let's move on to the Carnot refrigerator and heat pump. Okay, from the previous lesson, we have studied that the COP, the coefficient of performance for refrigerator, 1 over QH/QL, right? And COP of the heat pump is 1 over 1 minus QL/QH. Now we are looking at the reversible. Yeah, the Carnot refrigerator of heat pump and all. Remember what I told you? We never look at Q, but we look at the temperature instead. Yeah, so this is the formula for Carnot refrigerator or heat pump. Yeah, okay. So let's look at the calculation here. We have 275 TL and TH is 300. Okay, so for a reversible refrigerator for COP, yeah, the value is 11, so you need to plug in the 300 and the 275 into the formula, the respective formula, then you can get the answer. Now if let's say the COP is 7, then this process is irreversible, because any value that's lesser than 11, it means it is irreversible. It means there are factors that is causing it to lose energy elsewhere. Whereas if the value is greater than 13, of course this is then impossible. Yeah, impossible refrigerator. Okay. Okay, so this is the summary. Like previously, if the COP of your refrigerator is equals to the reversible, then it is a reversible refrigerator. If it's lesser, it's irreversible, and if it's greater, it is impossible. Yeah, okay, so that is the end of this chapter. But before I end the chapter, I would just like to discuss another question, yeah, on the Carnot heat pump itself. Let's solve this question. A heat pump is used to heat house during winter, as shown in figure 6.53. Let's look at figure 6.53. Where is figure 6.53? Okay, that is the figure. Yeah, so this is 6.53, figure 6.53. Okay, so what we have here, the house is maintained at 21 degrees at all time. 21 degrees at all time. The house is estimated to lose 135. So it's losing 135. Yeah. So when it's losing means this would be the Q, isn't it? Yeah. This would be the temperature. Yeah. Okay. So when the outer temperature drops to -5. -5 once again is temperature T. Determine the minimum power required to drive the heat pump. So we are looking at the COP of the heat pump itself. So for a COP, the formula would be 1 over 1 minus TLTH. So you get your COP as 11.3. Okay, so it says that it releases, yeah, losing heat at 135 kilojoule per hour. You change it to kilowatt, is 37.5. Okay, so use 37.5 above here, divided by 11.3, and then you get 3.32 kilowatt. So thank you for listening. So that would be the summary of the lecture.